Life on Earth runs on rhythms. Day follows night, autumn slides into winter, and the tides roll in and out along every coastline with almost mechanical precision. Many of these changes happen quickly enough that we can observe them, measure them, even predict them down to the minute. But there are other cycles, ones that play out across enormous stretches of time, and those are far harder to get a handle on. Take the Milankovitch cycles, for example. These are the slow, grinding shifts in Earth's orbit and axial tilt that drive the coming and going of ice ages and warm interglacial periods. They unfold so gradually that no single human life could ever perceive them directly. You would need to be around for tens of thousands of years just to catch one complete swing. But there is another climate cycle, one that almost certainly will touch every single person alive today, and probably more than once in a lifetime. It goes by the names El Niño and La Niña, two phases of a single interconnected phenomenon known by its full scientific name, El Niño Southern Oscillation. The ocean gives birth to it somewhere deep in the tropical Pacific, but its effects ripple outward across the entire planet like a stone dropped into a pond. Over recent decades, those ripples have grown harder and harder to ignore. Floods have washed away entire neighborhoods. Droughts have scorched crops down to bare earth. Fish have vanished from waters where generations of fishermen relied on them. And coral reefs, those extraordinarily complex underwater ecosystems, have died off at a scale that once seemed almost unimaginable. In 1998, one of the most powerful El Niño episodes ever recorded triggered a mass bleaching event that wiped out roughly 16% of all coral reefs on Earth. The damage from that single event is still echoing through ocean ecosystems today. El Niño Southern Oscillation is not some regional weather quirk. It is a truly global system, and its influence reaches into the lives of people on every continent, whether they know it or not. To really understand what this phenomenon is, it helps to start at the very beginning, even with the name itself. If El Niño sounds more like a character from a folktale than a term from a climate science textbook, that is actually not far from the truth. As far back as the 15th century, fishermen working the waters off the coast of South America began noticing something strange. Around Christmas time, the ocean near the shore would turn noticeably warmer, and the fish they depended on would simply disappear. Their catches would collapse, and this pattern seemed to repeat itself every few years with an almost eerie consistency. The fishermen gave this mysterious warming a name, El Niño de Navidad, which translates roughly as the Christ child or the Christmas child. It was a simple, almost poetic name for what would eventually turn out to be one of the most powerful climate-driving mechanisms on the entire planet. Something about naming a disruptive, periodic force after a newborn child feels quietly appropriate. There is something both gentle and unstoppable about it. Centuries passed before scientists began piecing together the full picture. In the late 19th and early 20th centuries, researchers started noticing that unusual weather events in wildly different corners of the globe seemed to be happening at the same time. Droughts in India, torrential rains in Peru, extreme heat in Australia. These were not random coincidences. They were starting to look like the fingerprints of something much larger. By the middle of the 20th century, the scientific community had connected the dots. These events were all phases of a single, recurring global cycle. And so the concept of El Niño Southern Oscillation was born. On average, one complete cycle takes about 5 years from start to finish, though the actual interval can range anywhere from 2 to 7 years. Climate systems, it turns out, are not fond of keeping a strict schedule. To understand why this whole thing happens in the first place, you need to picture what the Pacific Ocean looks like under normal, undisturbed conditions. Along the equator, winds blow constantly from east to west. These are called trade winds, and they owe their existence to the rotation of the Earth, specifically to something known as the Coriolis effect. Think of it this way. If our planet were perfectly stationary, air would simply flow straight from the poles toward the equator, moving from high-pressure regions down into the warm, low-pressure tropical zones. But the Earth is spinning, and that spin deflects moving air sideways. In a band roughly 30 degrees north and south of the equator, a zone that old-time sailors once called the horse latitudes, Air in the northern hemisphere curves toward the southwest, while air in the southern hemisphere curves toward the northwest. The result, where those two flows meet near the equator, is a reliable, persistent set of east to west winds, the trade winds. And these trade winds are not just an interesting footnote in a geography textbook. They are doing something critically important. They are physically pushing warm surface water westward across the Pacific, away from the coasts of South America and toward Asia and Australia. The warm water piles up on the western side of the ocean, and on the eastern side, where that warm surface layer has been pushed away, cold water from deep in the ocean rises up to take its place. This process is called upwelling. Now here is why upwelling matters so much. Cold water rising from the deep carries with it an enormous load of nutrients. Those nutrients feed phytoplankton, microscopic marine plants. The phytoplankton feeds small fish. The small fish feed larger fish, seabirds, marine mammals, and ultimately, the fishing industries that entire coastal communities depend on. The rich fisheries off the western coast of South America, some of the most productive in the world, exist precisely because of this cold, nutrient-rich upwelling. The entire ecosystem is built on it. Now imagine that system starts to break down. That is exactly what happens during El Niño. The trade winds weaken, sometimes dramatically. The warm water that normally gets pushed westward stops moving or even starts to drift back eastward. It accumulates along the eastern side of the Pacific, off the coasts of North and South America. The upwelling of cold, nutrient-rich water slows down or stops altogether. Phytoplankton populations crash, fish either migrate or die, and the massive pools of warm water and warm, moist air that used to sit over the western Pacific shift far to the east. The weather consequences are felt almost immediately, and they spread across the entire globe like a chain reaction. The Pacific jet stream, a fast-moving river of air high in the atmosphere that cuts across North America, shifts southward. The northern United States and Canada experience warmer, drier winters than usual. Meanwhile, the Gulf Coast of the United States and much of South America's Pacific coastline get hammered by heavy rainfall. In Peru and Ecuador, where rain typically falls between April and October anyway, a strong El Niño year can tip the situation into outright catastrophe. The 1997 to 1998 episode, one of the strongest on record, unleashed devastating floods across Peru. Bridges collapsed. Entire shantytown neighborhoods were buried under a meter of mud. Around 250,000 people lost their homes. The Tumbes region in northern Peru, which is normally an arid, near-desert landscape, received 16 times its average annual rainfall in that single year. 16 times. That number is almost impossible to visualize if you have ever stood in a dry, dusty landscape and tried to imagine it drowning. But the Pacific coast of Latin America is just one dot on the map of El Niño's global reach. While South America drowns, Southern Asia and Australia go into drought. India has recorded some of its most devastating famines in direct connection with the weakening of the monsoon during El Niño periods. Australia, already one of the driest inhabited continents on Earth, essentially transforms into a tinderbox. Australian wildfires are among the most destructive on the planet under normal conditions. When El Niño is hovering over the country, the fire risk multiplies several times over. Just consider the year 2020. That was actually a year without a significant El Niño event, and yet the fires that season burned through roughly 20 million hectares of land. The images broadcast around the world, the deep crimson sky hanging over Sydney, rivers of people fleeing walls of flame, are burned into collective memory. So the question that genuinely alarmed emergency officials and climate scientists alike was this: what happens during a truly powerful El Niño year when the full force of this natural system is unleashed? That question alone was enough to make forecasters watch the Pacific with deep unease. At the global scale, years with strong El Niño conditions push the average surface temperature of the Earth up by roughly 1 degree Celsius. That might sound modest at first, just 1 degree, but in the context of, and here is something worth keeping in mind, Not every El Niño event hits with the same force. The average duration of a single event runs somewhere between 9 and 12 months, though in rare cases, these cycles have stretched out over several years. Earth's climate is an extraordinarily complex system with dozens of interlocking variables, which is why no two El Niño events are ever truly identical. Scientists always measure their impact relative to what the weather would have looked like without them, a kind of invisible baseline that helps us understand just how much these ocean-atmosphere swings actually matter on a planetary scale. Now, La Niña is the other side of the same coin. If El Niño is the warm phase, La Niña is its mirror image, though interestingly, it can still bring rising temperatures to certain regions. Where El Niño weakens the trade winds, La Niña supercharges them. Think of it this way. El Niño is a deviation from normal conditions in one direction, while La Niña is essentially an amplified version of normal. The trade winds blow with twice their usual strength, pushing warm water even further from the coasts of South America toward Asia. Along the American coastline, the upwelling of cold, nutrient-rich water from the deep ocean becomes even more intense than usual. For marine ecosystems, this is essentially a feast. Plankton blooms in enormous quantities, fish travel in massive schools, and cold water species, including salmon, push into waters that would ordinarily be far too warm for them to survive. It is remarkable, really, that creatures adapted to frigid temperatures can suddenly colonize stretches of ocean that would have been completely inhospitable just months earlier. And it is not just fish. Squid also shift their migration routes in response to these temperature changes, following the cold water like a moving highway. Over in Asia, the story is completely different. The influx of warm equatorial water during La Niña creates not drought, as El Niño does, but the exact opposite: elevated humidity and torrential rainfall. This surge in moisture also drives a sharp increase in tropical cyclones, which form and intensify over superheated ocean surfaces. More heat in the water means more energy available for storms, and La Niña years in Asia can be genuinely dangerous for that reason. North America feels the effects too, and quite dramatically. The jet stream, that powerful river of air flowing through the upper layers of the atmosphere, shifts northward during La Niña, and that single shift rewrites the weather map for the entire continent. The southwestern United States falls into drought conditions, while the Pacific Northwest gets drenched with heavy precipitation. In 2022, La Niña helped trigger a megadrought across the American Southwest that turned out to be the worst in 1,200 years. 1,200 years, longer than the existence of most modern nations. You can actually see the evidence of this in satellite photos of Lake Mead, the reservoir behind Hoover Dam. There is a pale white stripe running along the exposed shoreline, what geologists and locals call the bathtub ring. Under normal water levels, that rock is completely submerged. The drought stripped the lake back so far that it exposed geological layers that had not seen sunlight in decades, leaving behind a stark and silent record of just how severe the water deficit had become. Since we are already talking about trade winds and jet streams, we have to address how La Niña affects hurricane season, because the answer really depends on which ocean you are looking at, and the contrast could not be more striking. In the Atlantic, La Niña years tend to produce especially brutal hurricane seasons. The northward shift of the jet stream destabilizes the atmosphere over the South Atlantic, creating near-perfect conditions for powerful storms to develop. Meanwhile, in the Pacific Basin, the picture flips completely. Hurricane activity drops noticeably. This contrast is a perfect illustration of how a single planetary phenomenon can produce wildly different outcomes depending on where you happen to be standing. And Pacific Coast residents should not get too comfortable, because El Niño works in exactly the opposite direction and can deliver some genuinely unpleasant surprises to their shores. Along the Pacific coast of South America, La Niña years bring none of those warm Christmas-time waters that originally gave El Niño its name. El Niño, meaning the Christ child, or simply the child, a name given to it by Peruvian fishermen who noticed the warm current arriving around the holiday season. It is not a coincidence, then, that those same fishermen gave La Niña's opposite character the name El Viejo, the old man. The nickname captures the personality of the phenomenon perfectly. The weather grows colder and drier, and droughts can sometimes reach threatening proportions. In Brazil, particularly in the northern part of the country, La Niña brings a period of elevated rainfall from December through February. In the lowlands of Bolivia, it can mean catastrophic flooding, the kind that sweeps away entire villages and destroys infrastructure that communities depend on. Africa during La Niña years experiences conditions that are almost a mirror image of what El Niño delivers. Eastern Africa typically suffers through drier than normal weather, while Southern Africa tends to receive more rainfall. Rivers run fuller, farmland turns green. It is yet another reminder that these cycles do not affect every corner of the world the same way. So where are we right now in this endless cycle? The National Oceanic and Atmospheric Administration, the United States agency that monitors these patterns, confirmed the end of a prolonged La Niña that had lasted a full year and a half. Scientists reached that conclusion by analyzing the difference in atmospheric pressure between the western and eastern sides of the Pacific Ocean. That measurement is called the Equatorial Southern Oscillation Index, and the most recent reading came in at just 0.1, compared to a value of 1 just a year earlier. In practical terms, conditions have returned to something close to neutral. It is too early to make definitive calls, but there are already signs that El Niño could make its presence known in the near future. According to projections from the National Oceanic and Atmospheric Administration, the probability of El Niño returning was estimated at 60%. If it arrives, the consequences will be significant. India, for example, had already begun warning its population about the possibility of reduced monsoon rainfall and the risks that would bring to agriculture and water supply across the subcontinent. There is another reason to expect El Niño's return, and it comes directly from the historical record. Since scientists began systematically tracking these cycles back in the 1950s, the longest gap ever recorded between two El Niño events has never exceeded 4 years. If this one simply fails to appear, climate science will be looking at an unprecedented 5-year gap, something that has never happened in the entire observational record. That alone would be a remarkable and somewhat unsettling anomaly. All of this is a powerful reminder of why studying climate cycles matters so deeply, not just as an academic exercise, but as something that directly affects human survival. And the implications stretch far beyond our own planet. The better we understand the feedback loops connecting the atmosphere, the ocean, and the biosphere here on Earth, the better equipped we will be if humanity ever seriously turns its attention to transforming other worlds. Terraforming Mars, Venus, Mercury, the Moon, or perhaps a distant exoplanet somewhere deep in the Milky Way, all of that will require precisely the skill we are sharpening right now. The ability to understand how climate systems interact, how a small change in one parameter triggers a cascade of effects across an entire planet. That day may feel distant, but it is never too early to prepare for it.